Hello, for Chapter 7 we're going to look at ensemble learning in random forests. And these are going to be ways of grouping together different machine learning models and using them together. So kind of the main concept here is that the wisdom of the crowd uh, might be better than the wisdom of one individual. And in this case, if we can create a number of different models and use them together, uh, eh, um, they can work out better. And um, these types of systems are getting very popular these days in almost every competition or uh, system. It often is using something like this. But what's nice is that it's not overly complicated often, and there are tools now set up to do this. It used to be requiring a lot of code to do this, but now there are systems in place to do most of this for us. So the first thing we're going to look at is voting classifiers. And again, the idea here is that we have a set of different machine learning models, and we have them vote, and then whichever ones have the most votes or closest votes win in some ways, or classify things. So that's kind of our idea, is to do some sort of voting. So let's look at the code for that. So let me go back up here, sorry. So this is chapter 7's module, and again we're importing a whole bunch of libraries from SK scikit-learn here for a bunch of different classifiers, and then ways of merging these classifiers together. We're also going to be using our iris database again, so we'll be importing that here. So I've imported that already, and here's the basic flowers again. So we've got 4 different characteristics of each flower, and then one flower's the species. And so it's generally just a classification problem. Given some measurements, can we figure out which of the 3 types of flowers that is here. We're going to initially do our break with training and testing data, but we'll look at some alternatives but just so we know, there's 128 flowers, or there's 150 flowers in our database total. 120 are often broken up into the training, and then the other 30 are in the testing set. Okay, so the first thing we're going to look at is this voting classifier. So we're going to train a couple classifiers and have them vote together. So we're going to look at a logistics regression classifier, support vector machine classifier, random forest classifier, and a k nearest neighbor classifier, and then we can maybe vote have them together. So here's our setup. So we're creating 3 different classifiers: a logistics classifier, decision tree classifier, and support vector machine classifier, and setting up. So these are things that we learned about in the last unit, and we're just using them all together now. And then we're creating an ensemble classifier called a voting classifier here. And then we're just listing out, so each of these classifiers we're giving a different name: log, rand, and svm classifier. And so here we're just specifying those 3 classifiers, or in this case they're called estimators for this. So we just put them together. We can have as many as we want and list them all out as our estimators. Here we have 3. And now we're going to train, and we just train with our training data, and then we are going to score this with our scoring data. And again, this should perform better than any of these individual modules together. And so again, we can just run this and get a score for that. So it's getting about 96% of these values correctly for this. You might get different results depending on what data. When you did the split here, you might get a better train test split. So if we were to run this again and then go down here and run this again, we might get slightly different results for this. But again, this is a pretty straightforward. We just create different classifiers, have them vote together, and train them all at once. So just a way of combining an ensemble of that. So the next one we're going to look at is called bagging, and this deals more with how we set up the training data rather than the different models. So here we're going to actually use a bunch of different decision trees. So rather than using 3 different models here, we're going to use the same model multiple times. So again, we're going to, in this case, use a decision tree classifier, and we're going to make that put that in a bagging classifier. So we create a bagging classifier, and in that we specify what classifier we want, and we specify how many of them we want. So up here, where we only use 3 classifiers, now we're going to try 500 different classifiers, all of the same type. And each one is going to randomly sample 100 items from our database and run this. So again, we're going to run this, fit this with our training and testing data, but each one is going to look at different, not the whole training and testing set. And again, it's kind of limited here because we have such a small data set. This works much better when you have huge data sets with, like tens of thousands or 100,000 samples, and you can easily break them up in many different ways. But again, the idea is that we're dividing our data set into multiple different bags, and each of these classifiers, our decision tree classifiers, are being trained on a slightly different set of data, and then hopefully then together they will generalize very well. So again, we can score this and see how it's going to perform for us. And again, we're getting pretty good performance out of this model. So again, we're just looking at ways of combining different decision trees together, or I mean different models together. And the next one we're going to look at is called random forest, because again, here you can guess we're creating a whole bunch of decision trees, putting a whole bunch of decision trees together. So you can imagine that we would want to name that a forest. So let's go back, see how we're doing with the textbook. This just talks about some of this setting up a voting classifier, and again, we looked at that code already, and then talks about bagging and how that works. And again, a nice graphical way of showing how it's selecting different data for training each of the different classifiers or predictors, and then shows the code. And again, this is basically the same code we have in our model for that. One thing that is interesting is that sometimes decision trees overfit the data, so you can see kind of an overfitting of the data in with one decision tree here, where if you have a whole bunch of decision trees, you get a little smoother, more generalized solution. You still will lose some values sometimes, but again, it may generalize better overall. So now we're going to skip some of this stuff on auto bag and random batch and different ways of setting this up, and we're just going to go down to random forest. Because this way of setting up a set of bagging decision trees trained together, that has been kind of generalized. It's such a common solution, it's given its own name basically, and that is random forest. So the random forest is basically just a bagging method with multiple samples of the data here. And so it just the code is just a little more streamlined. The decision trees are assumed as part of this model, where with the normal bagging you can use any sort of model. With random forest, it's assumed using decision trees. So here's our code for that, and we can train that. So again, in our code here, here's our random forest tree. And again, it's very similar to this. We still have a number of estimators here that we're working with and set up. But again, now we can also specify directly some of the settings for the decision tree, like the max leaf nodes for this. So we set up a random forest classifier. So this is creating 500 decision trees, and then we're going to train this. Let me just run that. And then we fit that to the training data, and then we do a score with our test data, and we get our model here. And again, we're working with relatively simple data sets. I'm using that because again, it'll let us run through this relatively fast. If you had large data sets and stuff, you could be spending hours training these systems. So it wouldn't be uncommon if you're especially training 500 different estimators of this size of decision tree. That would take a significant amount of time to pay, especially for large data sets here. So one of the reasons we're limiting that, and so our results are not that exciting here. We're not seeing a bunch of improvement for this because again we're working with a very minimal data set for this. But we will see this in the future when we get to larger data sets for this. So. Okay, and then I want you to do a little research on random forest, and in the write-up here for Unit 2, just articulate what are some of the advantages of random forests over decision trees, and then what are some of the disadvantages of random, or find at least one disadvantage of random forest over a decision tree, knowing that a random forest is just an ensemble of a whole bunch of decision trees. So when might you want to use that, and when might you not? And again, remember that we're using a really small data set here, so this is going very quickly, but that's not always the case. So. Okay, let's talk about boosting and how that is going to work. So the idea of boosting is not just to create a whole bunch of different and separate models, but to kind of link these together. So you train a model, and then based on where that model fails, you train another model to help improve the previous model. The most common way of boosting used today is something called ADA boosting. Okay, so the principle of ADA boosting is that we first train a base classifier like a decision tree to make a prediction. So that's what it's showing here. We're using it to train the data. And then we make some predictions and see how it goes. And then we create a new model, and we on the data, but we highlight the samples we got wrong in the original model. So although it might see all the training data, it will see some of this. So rather than maybe training all the data on it 10 times, we might train it on the ones we got wrong 10 times and the other ones once or twice or something like that. So again, we're not going to go into the numbers of how this is calculating how we weight the different things, but we will weight the runs we got wrong correctly. So again, you kind of see this model where our original thing predicted things right, but there was one sample that we got wrong here, and so in the next training model we will highlight that one sample we got wrong and try to create a new model, and then we'll unify those two models together and see where they get wrong again, and again we'll highlight the data that the new combined model gets wrong. So each subsequent model is trained on the samples which the previous models failed to classify correctly. And again, this used to be very difficult to have to compute. You had to write these models, determine which ones are wrong, put those in the separate array or bag, and retrain your models and all that stuff. But again, nowadays this is all done for us for this. So let's look at our code here. So ADA boosting here. So again, similar kind of structure with our other Ensemble learning. We just create an ADA boost classifier, kind of a meta classifier here, and then we specify what classifier we want. And again, here we're using decision trees, but we could use SVM and other things, and later on we'll look at neural networks and other more complicated models here. But here we're just using a decision tree classifier, and again we can specify parameters for that. And then we're going to use 200 different models here for this. And then we're going to fit this, and I'm not going to worry too much about some of these parameters here. Again, if you want to get more into ADA boosting, you can certainly learn more and stuff like that. We'll certainly even talk about learning rate more when we get to deep learning and neural networks, but the learning rate for now, you can just imagine it as how quickly it's training the model for this. So once we get this model set up, we then fit it to our data, And again, so it'll create a model, create another model, and train it on the items it's got incorrect and so on for this. So we'll fit this to our training data, and then we'll score it and see how it scores for this. So that's our general setup for this boosting method. So let's jump back into the textbook and kind of see where we're at. So it's trying to show you a little bit, like I say, the learning rate. If you have a fast learning rate, like a learning rate of 1, it will change how quickly each model views the data here. And you might jump around a little bit too much. A little slower learning rate will hopefully make small incremental changes of each model. And so again, in our case, we have 200, right? We had 200 different estimators, so it would be fine to have a slow learning rate, even slower than this if we wanted. So, okay, we're not going to go over some of this math on how we weight and do these predictions and that sort of stuff. That's kind of beyond the scope of that. If you're interested, you can certainly look up that, and there's a number of good tutorials online on this. But again, here it's talking about this process here. It talks a little bit about this SAM stage-wise additive model for a multi-class exponential loss function that's being used here. But again, we're not going to go that. I just really want you to understand what ADA boosting does. And ADA, that it trains a model and then trains the next model using the samples that were, by stressing the samples that got wrong in the previous model, and then the next model is trained again by stressing, spending more time learning with the samples that were misclassified on the previous models for that. Okay, let's talk a little bit about the other models. And again, we're just going to mention these, but we're not really going to go into these. Gradient boosting is another way. And again, similar to other ideas, again, we train a model and then we train a new model, not on the where ADA boosting trains it on stressing the examples that were on here. We actually calculate the error, some measure of how things were wrong, and so we are creating a new predictor based on what's called the residue error of the previous predictors for that. And so just another way of training these sequential versions of it. And again, we're just not going to go over that in this course. And again, there's one more, the stacked, let's see, where you can stack different models together and set that up. But again, we're really limited on time, and I want to make sure we get enough time to spend on deep learning, because so much of machine learning now is focused on deep learning. So we're going to push through, and we're going to just kind of skip over gradient boosting and stacking here as other ways of combining these models. So I did mention that these models, these methods are used a lot to win competitions or stuff. So I want you just to read 2 articles on it and to summarize a little bit of what that is in your write-up for this unit.